All right, so hello again. Let's jump into set 24. We are still working on vibrations and waves, simple harmonic motion. All right, so let's see. We've got 37, 54, 56, 75, 37. Clock is constructed so that it keeps perfect time when its simple pendulum has a period of 1 second at locations where G equals 9.8. The pendulum bob has a length of L equals 0.2482 meters. And instead of keeping perfect time, the clock runs slow by 1.5 minutes per day. What is the free fall acceleration at the clock's location? All right, so that was a mouthful. Let's start with what we always start with. And what are we looking for? We are looking for acceleration. What we're really looking for is how the acceleration is different than 9.8 meters per second squared. Because if it was 9.8 meters per second squared, it's saying it would keep perfect time. All right, so what do we know? We know period when it has perfect. When it has perfect time, we know that the length equals 0.2482 meters. And we have a running slow time. So we have a delta T equals 1.500 minutes per day. And you know we're going to change that right away. So we've got 1 day. It's 24 hours. You know what? Let's get rid of this and just do this. That's kind of messy looking. Oh, somebody's having a fun game of tag out there. 1 hour is 60 minutes. And 1 minute is 60 seconds. And if you punch that into a calculator, you get 0.00100416. All right, so our period when our time is perfect, plus our period when our time with our delta T is going to give us what our period is when, you know what, let's write down the equations that we know. I'm jumping into solving the problem before we do what we always do. So we know that T equals 2 pi over omega. And we know here that omega for a pendulum is G over L. For us, it would be AF over L. What else do we know? We know that, we know this because we always know that. Whether it's useful or not, we'll find out. We know this. What else do we know? What else do we know? I think that's all that we could potentially use to solve for this. Okay, so let's do T. Let's find out what our new period is. T omega. And we know that omega is this here. So equals 2 pi over L. And like I started to say and then cut myself off because I was just jumping into it without following our process here. So our T is not what they give us. What they've given us is the T if our clock is running perfectly and we know that it's not. So our T that we're looking for is going to be our T perfect time, which is what's given, plus our delta T. So we're going to have T equals our perfect time. Sorry, plus delta T. And that's 1 plus 0.0010416. 1 point. All right, so we're solving for this. So let's rearrange and solve for that. We're gonna have to square both sides to get rid of our 1/2 here. So we end up with AF equals 2 pi squared over T squared. That will be here, L. And of course, we have T as this. So we're going to plug in what we know. What was L again? 0.2482 squared. And our T is 1.0010416 squared. And you end up with 9.7785. We've got a lot of significant digits here, and we've got a lot of significant digits here because if we only had 2 or 3, like we're usually given, what we end up with is 9.80. So what they're trying to show here is that clocks that are not very far away from what we consider the perfect center of gravity are going to run slightly off. And by run slightly off, 1.5 minutes per day. So, and I don't mean like, you live at, 10 meters above sea level or anything. It's significantly far away, but not, and this is it's very close to 9.80 meters per second squared. Anyway, okay, so using our significant digits, which are 4, we get 9.779 meters per second squared. All right, B asks, what length of pendulum bob is required for the clock to keep perfect time? Oh, I didn't do B online. I gotta fix that. So L equals question mark. I was like, gosh, I don't remember solving this. All right, so if our T is 0.000, right, S, and G equals 9.80 meters per second squared. And we have our unknown is L. Okay, that's enough to solve this. Okay, so our equation is 2 equals 2 pi over omega equals 2 pi over G over L. We're going to square both sides, and we're going to get T squared equals 2 pi squared. We're solving for L. So we get L equals T squared G all over 2 pi squared. I didn't solve this before, so give me a moment here to grab a calculator and do the math here. Well, let's write it out. Oops. 9.8 over 2 pi squared. Okay. So pi squared There's my calculator not. Calculator's broken. It's not working. That's weird. All right, and we get 0.24773, blah, 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 or L equals 0.2477 meters. Sorry, that one was ugly because I didn't solve it in advance. All right, now we're moving along. 254. Reads, an astronaut on the moon wishes to measure the local value of G by timing pulses traveling down a wire that has a large object suspended from it. Assume a wire of mass 4 grams is 1.6 meters long and has a 3.00 kilogram object suspended from it. A pulse requires 36.1 milliseconds to traverse the length of the wire. Calculate G of the moon from this data. All right, so we got this big old mass here, and we're sending pulses down it and we're timing it. And this is L. All right, so what are we given? Well, first, are there A's and B's? Need to do that because for the last problem, I forgot to do B. So we are looking for G of the moon, and we are given the mass of our object. Oh, I'm sorry. The mass of our object is 3.00 kilograms. The mass of our wire is 0.004 kilograms. We're given L equals 1.6 meters. Oh, I gotta make sure I do that here. What else are we given here? T equals 0.0361 seconds. I think that's everything we're given. All right, so I don't know, just the fact that we're given the length of something and the mass of it, that almost always means that you're going to have to find mass per length or mass per volume or whatever. And so right away, you can just go mu equals the mass divided by the length. Can wait to the end if you want to do that, but oh, sorry. Oh no, that's right. Okay. I was looking at the mass of the object. I should do something like that to make sure I've got it. Okay. All right, so we're looking for G. So let's write down the calculations that we know. We know this. We use that one a lot, huh? We know that. We know this. And we know this. All right, so can stick that in there, but for us, this is going to be gravity. So B equals mg all over mu, and Am I doing this correctly? Oh, yeah. Oh, duh. Oh my gosh. I didn't write this down, but I should. So velocity is meters per second, right? And so we can do, we've got this and this. So that, oops, that equals 1.6 divided by 0.000361. Sorry, I kind of lost it there for a second. So we're going to rearrange to solve for that. Of course, we're going to square both sides, and we end up with G equals B squared mu all over M. And we get that 1.6 all over 0.361 squared. We get 0.004 over 1.6 all over plug it into your calculator and you got 1.63698, or gravity of the moon is 1.64, and that is what we'd expect. That is about 1/6 of what we see, and I'm sure you've all heard that gravity on the moon is roughly 1/6 of on the Earth. Is there a No, there's not. Okay. Gonna say if there a B to it. No, we're good on that one. All right, 56. Moving right along. 56. A string is 50 centimeters long and has a mass of 3 grams. A wave travels at 5 meters per second along the string. A second string is the same length, but half the mass of the first. If the two strings are under the same tension, what is the speed of a wave along the second string? Okay. So what have we got here? We've got string 1, we've got L1. Well, right, let's start with what we need. We need V2. V2 is question mark. We've got L1, 0.5 meters. We've got M1, 0.003. V1, M2, well, let's just do L2 has the same length, but half the mass. So M2 is going to be M1 over 2. All right, so we know this. And I'm thinking that's all we need to solve this. Yeah, I think that's all we need to solve this one. Okay, so V equals the square root of F mu. Mu1 we'll just do right away because we're going to need it. And that is 0.003 all over 0.5. 2 is M1. All right, so two strings are under the same tension. Okay, so F1 equals F2. I know I was missing something that I needed to write here. All right, so we can write that V squared 1 mu1 equals F. But we know that F1 equals F2. So we can also say that V squared to mu2 equals F, and then we can set them equal to each other. And we are looking for V2. Okay, so V2 squared equals V1 squared mu1 all over mu2 square root. And if we plug in the values that we were given, we get 5 squared 0.05. Why did I do that? So the reason that I do this is because these frequently in these problems things end up canceling. So if we put like M1 in here, and then we write M1 divided by 2, we can see that these cancel out. And this in a problem like this, or in your problems for your tests and quizzes, is probably not super important, but when you are solving a enormous task that you have to solve really, really quickly, these sorts of things are really important. Or if you're solving a big problem where you have to cancel, where you end up with this enormous algebra, it's really important to be able to know what you can cancel out. And so when you see something that says it's half of, leave it as M1 over 2. All right, so plugging in what we know, taking the square root of, we end up with 7.071068, or V2 equals 7.07 meters per second. All right, that was 56, 75. All right. Oh, an elevator problem. 2 kilogram black hangs without vibrating at the end of a string that is attached to the ceiling of an elevator car. All right, so elevator. The car is rising with an upward acceleration of g equals 3 when the acceleration suddenly ceases at t equals 0. All right, so A, we're looking for omega. what do we know? We know that M equals 2 kilograms. We know K equals 500. We know A equals 2/3. That's all we know. All right. So what is the angular frequency of oscillation of the block after the acceleration ceases? So this is really simple because we know that if we don't have if we don't have this acceleration, we know this. And we're given both of these. And so we end up with 15.8114 radians per second. All right, so that part was simple enough. So now this is where it gets interesting that we need that G/3. By what amount is the spring stretched during the time that the elevator car is accelerating? Okay, so what else do we need to know here? We need this. Oh, let's write down what we're looking for first. We are looking for X. Question mark, not 0. And we know this. So at a time where the car is going up, the spring is pulling it up, gravity's pulling it down. So we're going to say that our forces, let's put a T there, like our total forces together are going to be the spring constant, or I usually do FH for Hooke's law, minus mg. They just have to be opposite of each other, really, because they're pointing in opposite directions. Okay, so we know F equals ma. We know that FH equals kx. So ma equals kx minus mg. We're looking for this guy. Let's rearrange to solve for x. And we get x equals m a plus g all over k. Now, usually we would say that a plus g equals 2g, but we know here that our acceleration upward is a real acceleration and is not g, it's g/3. And so we will have g/3 plus g all over k, or m g/3, and we've got m is 2, g is 9.8, 3k is 500. Plug that into your calculator and you get 5.523, and it actually is what we're looking for, 3 significant digits. All right. That was 75. Oh, we're done. All right. See you next time.